Chapter 18 is carboxylic acid derivatives. Chapter 19 is enolates, enamines, and Michael addition. In Chapter 18, there are 8 important topics to talk about, and we are going to go one by one, mentioning them in order that they were brought up both in lecture and in 2 textbooks that will be referred to throughout the discussion. 1, the Brown textbook, and 2, the Klein textbook. Alright, let's get into it. The first topic of carboxylic acid derivatives is hydrolysis. Hydrolysis is a reaction with water where something breaks apart. So we talk about 4 species that will undergo hydrolysis when it comes to carboxylic acid derivatives. Now, what are these 4 species and why are they so important throughout this entire chapter? They are 1, acid chlorides. Acid chloride is the carboxylic acid derivative that replaces a hydroxyl with a chlorine atom. 2, acid anhydride. Acid anhydride is a carboxylic derivative that replaces the hydroxyl with a carbonyl and then an alkyl chain. Esters. Esters are the derivative that replaces your hydroxyl hydrogen with a new R group. Amides are the carboxylic acid derivatives where you replace the hydroxyl oxygen with a nitrogen. So that would be NH2, one bound to the carbonyl carbon. Alright, so what happens when we react these species with water? Well, generally, there's going to be a divide in the middle of these carboxylic acid derivatives, and that is due to their reactivity. So before the divide, you do not need any support from an acid catalyst or a base, and after the divide, you do need support on the acid by way of acid catalyst or by way of a basic mechanism. So number 1 is acid chlorides. The mechanism for the hydrolysis of an acid chloride is going to begin with the attack of the chlorine bound carbonyl carbon by water, which is a weak nucleophile. This attack occurs at the carbonyl carbon of the acid chloride because it is highly electrophilic, owing to its being bound twice to an oxygen and once to a chlorine, both highly electronegative atoms. Additionally, there is no acidic proton here for that water to react with instead. So the water will add right into the carbonyl, we get a tetrahedral intermediate, and here the leaving group is a chlorine, which is a very stable and quick to form leaving group. So this is the first of many such mechanisms in which the leaving group is attached first to the carbonyl carbon and then leaves, and the general umbrella term for these mechanisms is nucleophilic acyl substitution. Every mechanism we'll discuss in the carboxylic derivative chapter is essentially a nucleophilic acyl substitution. When it comes to acid anhydrides, which is the carboxylic acid derivative with the carbonyl right after the hydroxyl oxygen instead of the hydroxyl hydrogen, we are going to have the same exact mechanism, except that this time the leaving group is a carboxylate anion, which will need to undergo some sort of acid workup in order to form carboxylic acids for the product. Or actually, perhaps not, so when you react an acid anhydride with water, it forms your carboxylic acid as one product and the carboxylate anion, which then attacks the protonated carboxylic acid product. The reason your carboxylic acid product is protonated is because the water added in with both its protons and then one of them is removed by the carboxylate. So your product without any workup is 2 carboxylic acids. Now we reach the divide where we have to give help to our carboxylic acid derivative in order to have it react with water. So this divide comes at the esters. So there are 2 ways to hydrolyze an ester. One is the acidic pathway, and the other is a basic pathway. The acidic pathway, the first step is going to be the protonation of the carbonyl oxygen with a strong acid. So here you're going to want to use a strong acid like H2SO4. And then, once that carbonyl oxygen is protonated, the carbonyl carbon is highly electrophilic. The reason we needed to protonate it is because it wasn't electrophilic enough before to be attacked by a weak nucleophile like water. Then from there, the same mechanism occurs, except this time we're going to need a proton transfer to protonate the ester's oxygen to make it an alcohol, which will then leave. Before it leaves, it's going to be a protonated, positively charged intermediate with a positive on the oxygen, and then it's going to leave as an alcohol in solution. That's the acidic mechanism for ester hydrolysis. Then we went into the basic mechanism. And now, the basic mechanism is the one we are going to want to focus on, and that is due to a pretty important real-life application for that. So the basic mechanism for ester hydrolysis is going to be called saponification, and in this case, the water actually comes in the form of your OH bound to Na. So it's NaOH, so sodium hydroxide, really. The OH is a strongly anionic nucleophile, and thus the carbonyl carbon of the ester does not need any help from an acid catalyst here. Instead, we get a direct addition right into the carbonyl carbon, and the thing that leaves is actually the alkoxide anion. So when you draw this mechanism out, you'll see an alkoxide anion leaving and a carboxylic acid forming on the other side. So what happens when you have a carboxylic acid and an alkoxide anion? You need to keep going with the mechanism and show that alkoxide deprotonating the carboxylic. So the last step with saponification, with the basic hydrolysis of an ester, is going to be an acid workup, because you need a proton for that carboxylate anion. You cannot stop just with the leaving group leaving. Next is amides. Now, amides are very unreactive due to the nitrogen not being electronegative enough to pull on that carbonyl carbon, and also due to the resonance between the nitrogen and the oxygen on that functional group. So when the nitrogen bears a positive charge in one of the resonance structures, it is not as unhappy as when the oxygen might on, for example, an ester. So that resonance structure is going to be higher contributing, which makes the whole thing a little bit less electrophilic. However, if you have a strong acid, you can attack this functional group with water, which is hydrolysis, and convert it to a carboxylic acid. So here the mechanism is exactly the same, except the leaving group is going to be an NH3+, and your product is going to be carboxylic acid plus NH4, which is ammonium. Next is going to be the basic pathway for amides. Now, this is a pretty important mechanism to understand, because it is going to have the leaving group of the amide anion. Now, the amide anion is an N bound to two H's, and it is going to be the thing that is attached to our carbonyl carbon on the amide that is going to have to leave when you add in the OH from NaOH. So, the mechanism here requires that you form something that is less stable than kicking out an amide. What is that something? Well, first the OH adds in. The bonds go up to the oxygen on the amide. Then we have a tetrahedral intermediate with one negatively charged oxygen and then one OH that you just added in. Well, since we have a lot of OH lying around and a lot of heat, we're going to be deprotonating one of the hydrogens here. Well, the most acidic hydrogen is the one bound to the oxygen on the hydroxyl that you just added into your molecule. So that one is going to be deprotonated, and now we have two negative oxygens. Well, that's highly unstable, and so one of those oxygens is it's going to send those electrons down into a pi bond with the carbonyl carbon while kicking out the amide as your leaving group. That amide immediately reacts with water to become NH3, and then you need to do an acid workup in order to protonate your carboxylate anion, which is formed. Alright, so our next topic when it came to carboxylic acid derivatives was adding alcohols. So, adding water is the real name for hydrolysis, which is just a fancy name. But when it comes to adding alcohols, it's really a similar thing, and except we're going to need to be a little bit more specific with how exactly it happens when it comes to esters. But before we get to alcohols, I want to mention one more hydrolysis that may not have been covered in our lecture class, but was mentioned by Klein, and whose mechanism is actually closely related to the hydrolysis of all those other carboxylic acid derivatives that I mentioned before, and that is the hydrolysis of nitriles. Now, nitriles is the carboxylic acid functional group derivative where you have a C triple bound to N, highly unreactive due to N's stability when triple bound to a carbon. However, it can react if put under very acidic or very basic conditions with heat. So, in this mechanism, let's do the acidic one first. So acidic, the nitrogen on the nitrile is going to reach out and grab a proton. That causes a positively charged nitrogen, which will resonate with the carbon to form a stable nitrogen, and that carbon in that resonating will be attacked by a water. So it is the carbonyl carbon that needs to be attacked by a water. Now you have a water added into your carbonyl carbon and a double bond to N with H on your carbonyl carbon. This, after a proton transfer, is just the imine version of a carboxylic acid. So it's C double bound to NH rather than double bound to O. So that's a pretty great hint as to how this mechanism is going to proceed, because it's just going to be the hydrolysis of just going to be the conversion of that imine to the amide version. So I should have prefaced this, but the hydrolysis product of nitrile is not going to be a carboxylic acid. It is going to be an amide. You can't form a carboxylic acid directly from a nitrile. You need to form an amide first, and then go through further steps if you wanted to, for example, hydrolyze the amide, as we talked about before. So, sorry, you have this imine version of the carboxylic acid. That imine nitrogen is going to grab another proton from solution, become NH2, which is positive in this case, but also stable by resonance with the hydroxyl on the imine carboxylic acid that you formed. Well, that hydroxyl can donate its proton to solution to become neutral, and in that resonance form, your nitrogen actually doesn't have a double bond with the carbon anymore. So our goal is to get rid of that double bond to the carbon and put it between the carbon and the oxygen. And in order to do that, we need to draw resonance once the imine has picked up a proton. Now, the basic way to do the hydrolysis of nitriles would instead have the OH directly attacking the C. H2O does attack the C in the acid-based mechanism, but in the base catalyzed mechanism, it's going to be directly attacked, and then you have N double bound to C, and that C also bound to a hydroxyl. So similarly to before, you're going to have the N be protonated. You're going to have, this time, a proton removed from your hydroxyl oxygen. You're going to have that resulting negative oxygen move its electrons down. It's sort of similar to what we saw with the hydrolysis of the amides reaction, but this time, rather than kicking out the N, we're just going to put another lone pair on it, which makes it negative, but that negative N immediately attacks the water because negative N is highly unstable, highly basic. Okay, so that's the mechanism for nitrile. Seems kind of like it could be put on a test, so good to mention. All right, so let's talk a little bit about oxygen nucleophiles. So oxygen nucleophiles are going to attack carboxylic acid derivatives in a similar way to the water as a nucleophile. So oxygen nucleophile, I just mean alcohol. So with acid chloride, it's going to be the same mechanism, and the reaction from this, once you kick out chlorine as your leaving group, is actually going to be an ester. So with hydrolysis, the product is a carboxylic acid. With alcohol addition, the product is an ester, because if you think about it, you're taking a carbonyl and you're adding an alcohol to the end, which really is what an ester is. So acid chlorides, these guys are going to go right in and be turned into esters. Now, one thing I need to note that Klein points out about when you turn a acid chloride into an ester is the nature of the oxygen. Now, this reaction is going to rely on your oxygen not being very sterically hindered. So Klein reads, the OH group is said to undergo acylation because the acyl group has been transferred to the OH group to produce an ester. This process is sensitive to steric effects, which can be exploited to selectively acylate a primary alcohol in the presence of a secondary, more hindered alcohol. So they give the example of of your normal acid chloride, which is just the chloride version of acetic acid, and then they give this cyclic alkyl, so it's cyclohexane with two alcohol substituents. One of them is a CH2 and then an OH, and one of them is just the OH coming directly off of the cyclohexane ring, which makes it a secondary alcohol. So we have one primary alcohol, one secondary alcohol, and after the reaction occurs, you see that only one of them attacks our acid chloride, and that is the primary alcohol, because that one is not sterically hindered. So, interesting to note here that we did not mention in class, but that is mentioned by the Klein textbook. Steric hindrance comes into play when we're talking about the production of esters from acid chlorides and alcohols. Interesting. All right. I would assume that would apply for all of the other ones, which really is just acid chlorides, acid anhydrides, and esters that react with alcohols. Amides and nitriles do not react with alcohols. So, let's continue with acid anhydrides. Same reaction, except the leaving group is our carboxylate. I covered that same reaction with hydrolysis. Now, let's go to esters. So, when you're reacting an ester with an alcohol, you might be a little bit confused because we said that the product of reaction of an acid, carboxylic acid derivative with alcohol is an ester. Well, ester to ester? Like, what does that even mean? Well, we're going to have to use a little bit of Le principle here because the ester that we formed is just going to be whichever alcohol is more present in solution. So what do I mean by that? Well, say you have an ester which is an ethyl ester. So you have an ethyl group on the other end, and you really want a methyl ester instead. Well, you can add just a ton of methanol with acid or base, and the acid is just going to be the acid addition of a nucleophile to your carboxylic acid derivative, and then the basic mechanism is going to be a little different, but I'm going to explain. And then your result is going to be your your methyl ester. If you add a ton of whatever alcohol you want to add into the ester. So, important to note about the basic mechanism of an ester change, which is an ester reaction with an alcohol, which is called transesterification. The basic mechanism requires that the base you use be the same as the alcohol you're trying to replace. So, for example, in class we covered the basic mechanism of adding ethoxide to a methyl ester. So we have our methyl ester on the left, and we want to turn it into an ethyl ester. Well, we add as our base a lot of ethoxide, because what that's going to be is I meant you add as your base whatever ester you want produced, because what adds right in is going to be that alcohol, rather. Okay, so that's the base. It's going to become important when we talk about the enol reactions. Okay, so covered acid chlorides, acid anhydrides. Now, that's the same one. Okay, so adding alcohols to acid chlorides, easy. Anhydrides, easy. Transesterification, make sure that you add the right base, and the base you add should be the one needed to add into your ester. So you're going to want, if you have methyl and you're trying to make ethyl, add a lot of ethoxide. All right, nitrogen nucleophiles with carboxylic acid derivatives. There's one big caveat and a special thing to note is that, well, first of all, the only carboxylic acid derivatives that react with nitrogen nucleophiles are acid chlorides and acid anhydrides. It's just these two big guys. But they need two equivalents of amine in order to react. So, one equivalent is going to be to add in, just like the alcohols did, add into the carbonyl carbon and form your amide ester. But the second equivalent, which is really just a secondary amide, amine on an amide group, but the second equivalent of amine that you add into the reaction to make this happen is going to be used as a base. Why do we need a base? Well, if you think about it, the amine is highly sensitive to being protonated because they are very basic. So when you get this tetrahedral intermediate where you have your double protonated amine added into your carbonyl carbon, and before you've kicked out after you've kicked out your chlorine, you need something to then deprotonate your protonated product. So you're going to want to add two equivalents of your amine whenever you're reacting an acid chloride, an acid anhydride with amines. Two equivalents. One as a base, one as your new nucleophile. Now, here is another important thing to note, is that you can actually use esters to form amides, or amide esters rather, using nitrogen nucleophile, but it's only the basic method, and you're going to need a lot of your amine and a lot of heat. Amides and nitriles do not react with amines rather. They do not react with amines. All right, moving on to topic. So that was topic number 3, which is the rendezvous with acid chlorides and acid anhydrides and the amine group. Now, topic number 4 is acid chlorides and the carboxylate. Now, this really does deserve its own topic, because we move between these carboxylic acid derivatives, and we need to know how to get from each one to the other one. So we already talked about how to get from any of them to a carboxylic acid. All you got to do, add water. with either a base or acid, depending on if you're in the highly reactive group, acid chloride and acid anhydride, or in the little bit less reactive group, which is esters and amides and nitriles. Oh. So there you're going to need a little bit of help, but if you want to make a carboxylic acid, just add water, okay? But what if we want to convert between them? Well, we know how to make amides, right? We just add the nitrogen nucleophile. We know how to make esters. We just add the oxygen nucleophile. But how do we go from an acid chloride directly to an acid anhydride? One way is to react the acid chloride with the carboxylate anion. So this is going to take place where the carboxylate anion attacks the carbonyl carbon of your acid chloride. Now, why don't we ever usually use carboxylate anions as nucleophiles? It's because they're very weak nucleophiles. But when it comes to acid chlorides, they're so reactive that you're definitely going to see those carboxylate anions reacting right with the chloride. So that would turn your acid chloride into an acid anhydride. So, so the big point with acid anhydrides is going to be that you can make them from acid chlorides directly. Okay, so why don't I go now into the last subject when it comes to nucleophilic addition to carboxylic acid derivatives. So this is going to be carbon nucleophiles. Now, a carbon nucleophile is something like a Grignard or a Gilman or an organolithium compound, and those are anionic carbons that add right into electrophilic sites. However, we need to be very specific and selective when it comes to adding these guys to carboxylic acid derivatives, because some of them are too reactive, some of them are not reactive enough, and we need to be very specific and very careful. The only reaction using carboxylic acid derivatives that employs the use of a Grignard reagent, which is something attached to MgBr, some alkyl group attached to MgBr with that alkyl carbon being anionic, is an ester. And the product of that is a di-substituted nucleophilic addition. So it would actually be a tertiary product, because in order to have an ester, you need an R group already. So I'm just going to describe this really quickly and explain why it is that when you're putting an ester and a Grignard together, it adds twice. So you start with your ester and you start with your Grignard. Or your organolithium compound, because the Grignard and the organolithium are going to be similar in reactivity. First, the nucleophile is going to add into your carbonyl carbon just like we've seen. Then, your leaving group is going to leave, and in these basic conditions, the leaving group is going to be an alkoxide anion that can leave. Well, what's now in solution is a carbonyl and more of your Grignard or organolithium reagent. Well, those can add right back into the carbonyl that you just formed. So you've already added one R group in, you've kicked out an alkoxide, and now you add a second R group in. So you have now a tertiary alkoxide. So now Grignard can no longer react the initial substrate, and we protonate using H2SO4 acid workup to end up with a 3' alcohol, which is the product of Grignard and ester reacting. Now, there's one more reaction, and it needs to be kept real cold. One more reaction with the carbon nucleophiles, and it needs to be kept really, really cold. And when I say cold, I mean negative 78 degrees Celsius. And that is as cold as dry ice. So, as my professor at Brooklyn College explained this to me, you're going to take your reaction flask and put dry ice all around it to get it so cold, and then you're going to add in your reactants. And so what reactants are we talking about? We're talking about an acid chloride, the most reactive carboxylic acid derivative, and we're talking about organocupric, which is 2 alkyl chains, copper, lithium. So the Gilman reagent is the name of this guy, and it is copper lithium attached to 2 alkyl chains. But only one of them adds in. Only one of them adds in. The crazy thing is there's 2 alkyl chains on your organocupric reagent, only one of them adds in. However, the second one would add in, or a second equivalent of it would add in if we didn't control our reaction conditions, but we are going to control. So let me explain when you do control it, which is just having a very low temperature, what happens. So first you add in. You have your organolithium copper reagent add right into the carbonyl carbon of the acid chloride. The pi bond between the carbonyl carbon and the oxygen goes up to the oxygen, the chlorine is there, and now you have a new alkyl R group. Well, now we have a tetrahedral intermediate, and it turns out that if it's very cold, negative 78 degrees Celsius, this tetrahedral carbonyl This tetrahedral carbon intermediate is very stable. So in order to have the chloride, so you have your stable intermediate, and that's really what we wanted to achieve. We wanted to produce this in high yield, which we did at the low temperature. But now that it's produced, we have a situation where the chlorine is just going to leave. So if there's no more organic cupric reagent around to react with the resulting carbonyl of chlorine leaving, well, how do we make sure that, one, the chlorine leaves, and two, there's no more organocupric in the same step? Well, we add H2O with heat. We warm the reaction back up. So we start with negative 78 degrees, really cold, but then we warm it back up in order to, one, kick out the chlorine, two, protonate all your organocupric to destroy it. And our result is a ketone. So you just turn an acid chloride directly into a ketone, not an alcohol, not a tertiary alcohol like we did with the ester, but a ketone. So acid chloride plus organocupric, negative 78 degrees, equals ketone. Ester, carboxylic ester, plus organolithium or Grignard reagent at room temperature, plus acid workup equals 3' alcohol. Alright, big note here, we don't want to react an acid chloride with a Grignard. My professor said that was a very dangerous reaction to do, and you can imagine, given that Grignard is highly anionic and acid chloride is highly electrophilic. Alright, the last topic that is important to cover when it comes to carboxylic acid derivatives, chapter 18, is reduction. So, there is one reducing agent that can reduce any carboxylic acid derivative to an alcohol. And when I say any, I mean the ones that already have oxygen, which is the ester, the anhydride, and the acid chloride. When it comes to the amide and the nitrile, those are going to be reduced to amine. But what is this reaction? What is this reagent I've been hinting at this whole time? It is lithium aluminum hydride. Remember that lithium aluminum hydride? Well, remember, I'll explain it. Lithium aluminum hydride is the strongest reducing agent that we have discussed in organic chemistry 2 so far. We've also discussed this thing called sodium borohydride, where the hydrogens are attached to a boron rather than an aluminum, where they are with lithium aluminum hydride. However, sodium borohydride is less reactive than lithium aluminum hydride because the boron atom is more electronegative than the aluminum atom, causing it to hold on to its hydrides a little bit harder, and it's also smaller. So here we're going to want to use lithium aluminum hydride, the really strong guy, to attack any of our carboxylic acid derivatives. So with, for example, an ester, lithium aluminum hydride adds in, the hydride adds to the carbonyl carbon, you kick out the leaving group, which is an alkoxide, and then you add in a second hydride, right? We have a carbonyl plus LiAlH4, so carbonyl with lithium aluminum hydride, still a basis for reduction, and what does the reduction cause? It causes an alkoxide. Then we add water to protonate. Now, the one thing, and the same happens with the amide or the nitrile, right? You just add your hydride into your carbonyl carbon, and then keep adding that in once you form another carbonyl, because our leaving group leaves, and then you eventually reach your product once you add an acid workup. And for amide and nitrile, that's also a way to make an amine, but really the best way to do an amine is reductive amination, where we started with an imine and reduced it just to an amine. But here, this way, we're going to go all the way to an amine. But I wouldn't use this mechanism to make an amine. It's a little bit roundabout because you need to make a more reactive carboxylic acid derivative first. Okay, so what about if we want to stop at an aldehyde and not go all the way to our alcohol? Well, there's only one reagent in one scenario that we mentioned in class in which this would be possible. So that is to use this thing called DIBAL. So I found an article from Master Organic Chemistry that is very helpful for understanding what this reagent does. So the name of the reagent is diisobutyl aluminum hydride, DIBAL. DIBAL, as Master Organic Chemistry reads, DIBAL is a strong, bulky reducing agent. Reactivity-wise, it bears a lot of similarity to lithium aluminum hydride, LiAlH4, which I just mentioned. However, the thing that diisobutyl aluminum hydride is going to do instead is just add one hydride into an ester. So our reaction arrow is going to look like DIBAL with hexane solvent at negative 70 degrees, and it needs to be this cold, I would assume, to stabilize the intermediate aldehyde. So the Master Organic Chemistry blurb reads, the most notable reaction of Diebol is a reduction of esters to aldehydes. Unlike lithium aluminum hydride, LiAlH4, which reduces esters to primary alcohols, reactions with Diebol can stop at the aldehyde stage if the temperature is kept very low. The advantage of Diebol here is that it is more efficient. If we used LiAlH4, we would obtain a primary alcohol, which we would then have to oxidize up to the aldehyde using reagents such as PCC, so any of those oxidizing reagents. And here the mechanism is also worthy of note, because you need to understand sort of the mechanism to see why we keep it so cold. So it's going to be fast forward. It's going to be a similar thing to before, where we have this tetrahedral intermediate that we need to stabilize somehow. Well, what's going to happen is the carbonyl oxygen is going to attack the aluminum on the diisobutyl aluminum hydride. Then the hydride ion is going to attack the electrophilic carbonyl carbon, while the electrons from that carbon-oxygen bond go up to the oxygen, the pi bond. So you still have a sigma bond between the carbonyl carbon and the ester oxygen, or the oxygen, carbonyl oxygen rather, but now it is, the pi bond is turned into a lone pair that's on the oxygen. So this is stable at low temperature because it is a tetrahedral intermediate where the oxygen is attached to aluminum with two lone pairs, and then you have your ester alkyl group on the other side. So using an acidic workup, we can do two things. Probably one, neutralize the Diebol, but two, we can heat everything back up to kick out the leaving group, which is going to be the OCH3. And the OCH3 in this case coordinates to the aluminum, which is usually positively charged. So positive aluminum, negative O, and the CH3. All right. Same thing could be done, interesting, to nitriles to turn it into an imine, and then you can react that with H2O and HCl to form an aldehyde. Interesting. So you can go from a nitrile to an aldehyde using an imine, and then or using Diebol, and then H2O and HCl, which is just like a strong acid workup. Okay, the next topic is going to be, well, we've actually finished with carboxylic acid derivative. So the next topic is going to be enolates and enamines, which is chapter 19 from the Brown textbook, and that is also going to cover the Michael edition.